In this video, I'll be going over a problem related to the learning outcomes, explain experiments that show diffraction and interference, and solve problems involving two-slit and multiple slit interference. This question is specifically related to two-slit interference. The question comes from ACE Physics, syllabus code 9702, paper 22 from May-June 2014. Question number 7. It reads, a laser is placed in front of a double slit, as shown in figure 7.1. So here we can kind of see we got the laser, we've got a partition here that has a double slit in it. There's 2.8 meters between that double slit and a screen, and on the screen they've labeled that there are bright fringes everywhere where we see like one of these peaks. Furthermore, they've labeled two peaks, P and Q, and there are 12 millimeters of distance between those points. So that's sort of why it's not to scale. If this here is 2.8 meters, that's 12 millimeters, well, that can't be to scale. Here's an example of what this actually looks like in the lab, although with a green laser, and so its wavelength is closer to 510 nanometers or so. There you can see the interference fringes. We'll further see an example of how sort of not to scale we could actually make it. We'll take a lot of time to use this question as an opportunity to explore some of those learning outcomes. It says the laser emits light of frequency 670 terahertz. Interference fringes are observed on the screen. Explain how the interference fringes are formed. Part B says show that the wavelength of the light is 450 nanometers. Let's go ahead and just tackle this one right now because I want to kind of use the wavelength in my explanation up here, as I mentioned about how not to scale we can actually make this. So do you have an idea in mind about how we can go about showing the wavelength? Think about it. We know the frequency, right? And there's something special about light. It always travels at the same constant speed c. And that speed is about 300 million meters per second. So we can use 3.0 by 10 to the 8 meters per second. And in fact, you should use this value for the speed of light, not the more precisely known value, 299,792,458 meters per second. The reason for that is the speed of light is one of those data points that's given on as you sit for the papers here. Right, so use the value that they give you. The velocity of a wave is equal to its wavelength times frequency, and so that's also true for light waves. Because we know the frequency, we could calculate the wavelength, and it should be about 450 nanometers. Remember that 450 nanometers, the prefix nano is the same thing as 10 to the negative 9 meters. And so while this isn't, technically correct scientific notation, if you were to type that in your calculator, it might report something back like this, right? And so if we move the decimal point sort of back over here, then those two orders of magnitude are sort of balanced back out over here, right? So this is the same number. All right, if we plug in 3.0 by 10 to the 8 meters per second for the speed of light and divide it by the given frequency 670 tera is 10 to the 12, and then hertz is the same thing as a reciprocal second, so those units there will cancel, and we'll be left with meters. And hopefully our calculator shows us something that looks like that, the 450 nanometers that it asked us to show that the wavelength was that. All right, so we've got the speed of light, 3 by 10 to the 8, divided by 670 times 10 to the 12 terahertz, close parentheses, and we get 4.48 times 10 to the negative 7 meters, which is indeed about 450 nanometers. So good, it checks out. We've shown that the wavelength is about that. Right? So let's think about it up here. This laser has a wavelength equal to about 4.5 5, but I'll just keep the 4.48 by 10 to the negative 7 meters. All right, and it's traveling 2.8 meters to get to this screen. And so really, we could kind of think about as the laser hits this double slit, then the light waves are going to diffract at these gaps, at these openings. And so let's say that the light from this top, the light waves from this top slit here, and 450 nanometers, that's sort of right on the cusp of purple and blue here. And so keep in mind, this is one light source that we're starting with. And the way that lasers work is kind of tricky because we wouldn't probably be able to achieve interference if we used two lasers even tuned to the same frequency, or if they had the same wavelength, if they were the same color laser, because lasers kind of send out the light in packets, and so there can be a sudden phase change in a in that light, and so any sudden change of phase in the light pulses would be shared by both of the waves that are sort of emerging from the double slit if we use a single laser. And so sending one laser through a two slit is a way to get sort of two coherent sources. They have to have the same frequency, and that is going to have a constant phase difference over time, so the frequency is not going to change over time. So let's say this top slit, the light diffracts and makes it all the way up to, say, this point right here. And the bottom slit, let's say it diffracts and its light waves diffract all the way to a point, let's say, down there. Now the top slit on down here, let's say that its light waves diffracted all the way down to that lowest bright fringe right there. And the top slit made it all the way up, sorry, the bottom slit, sort of on the top side of it, the bottom slit diffracted its light all the way up to that highest peak that we see up here, somewhere like that. All right, well, here would be a point where the waves aren't meeting, okay? We're only getting sort of light from this slit that's sort of getting here, right? Because this wave only diffracted up to that point there, and so we see that sort of top bright fringe. Likewise, down here, there's going to be no interference because the waves aren't meeting there. That's just sort of where light from the bottom slit sort of made it down here, but the light from the top slit only had a chance to make it as far as this, and so that's where we see sort of the lowest bright fringe. So interference can only form where the two waves overlap. And because 450 nanometers is kind of like on the cusp of violet and blue, I'm going to show where they're overlapping in more of a bluish color here just to distinguish it. But keep in mind, this is the exact same light as we've talked about, right? And I'm going to kind of make it a little bit purplish too. But hopefully it'll be distinct, and I don't want to ruin the waveform over there. We'll work with that. So there you go. So where the waves overlap, that's where we'll observe the interference like we see over here. That's important to include in your explanation about how interference fringes form. Make sure that you include in your explanation that the waves have to be coherent, that is to say they have a constant phase difference, and they have to superpose to apply the principle of superposition. Let's take another moment to really think about what that means. We can calculate how many wavelengths there are for this laser light to get from here to here, because we know that it's traveled 2.8 meters. Thankfully, it's going pretty quickly, so it can make it there in almost no time at all. And we could calculate that time, but we'll save that for another day. If we have 2.8 meters of distance, and we have a wavelength of 4.48 times 10 to the negative 7 meters, then there's going to be 6,250,000 wavelengths to get from here, let's say, directly across to there. So let's say that this distance here, or rather there are 6,250,000 wavelengths, and I could show it with, sort of a waveform kind of like this, and I'd have to draw 6 million of them. Or I could show it with like a transverse wave and I could oscillate it 6 million times. I'll just sort of draw a line here, and you can imagine that there's 6 million tiny little variations like this in between here and here. Likewise, for this top slit, the wave that emerged from here had to go 6,250,000 of its wavelengths to get to this point here. But if we look at this central bright fringe, well, here maybe the wave had to go a whole extra wavelength. Okay, so it had to go 6,250,001 wavelengths to get there. And from the bottom slit, the wave emerging here had to travel 6,250,001 wavelengths to get here. So the path difference between the two waves to get to here is 0. Okay, the path difference is 0. If we look at this point here, well, here the bottom wave had to go an extra wavelength compared to this point. So the path difference is 1 wavelength. Again, a crest is going to meet a crest here because it had to travel just 1 extra wave. It already traveled 6 million waves, and it just went 1 extra one to get here. It had to go 2 extra wavelengths to get here. So when the path difference is some integer multiple of the wavelength, that's where we see constructive interference. And for light, that's observed as bright fringes. The dark spots in between the bright fringes we can think of as like this bottom slit. The wave that emerged there only went half of a wavelength longer to get here compared to this wave. And so a trough met a crest, and that's an example of destructive interference and dark fringes. And so we can include also in our explanation about how the interference fringes are formed, something about the path difference has to be an integer multiple of the wavelength, or the phase difference has to be an integer multiple of 360 degrees, because there's 360 degrees of phase in an entire wave. So you can think about it in terms of either path difference or in terms of phase difference. Coherent waves emerge from the slits and superpose. Where crest meets crest on the screen, we observe bright fringes. The path difference between the individual waves resulting in the bright fringe, and the bright fringes is an integer multiple of the wavelength. All right, so a couple of key ideas. You can either think about it in terms of path difference or phase difference. You need to make sure that you're mentioning that the two waves are coherent and that they have to meet, right? So there's no interference in these parts that I've kind of shown in the purple color, but only where the two waves meet, which I've shown in sort of a more bluish purpley color. But they are indeed the same wavelength, right? That's what coherent means. Same wavelength, same frequency, it remains the same over time. The question goes on to ask, the separation of the maxima P and Q observed on the screen is 12 millimeters. The distance between the double slit and the screen is 2.8 meters. Calculate the separation of the two slits. And so let's go back to our figure here and sort of think about everything we've got. This value here is what we call D. Or the quantity D is the distance between the slits and the screen. Its value is 2.8 meters for this question. Here, we're given enough information to calculate x, the distance between two bright fringes. The equation that is relevant for double slit or two-slit interference is wavelength equals ax over d, where a is the thing they're asking us to solve for in that question. It's the distance here between these two slits, so that's lowercase a. If we look between this bright fringe and this bright fringe, how many bright fringes are there that occupy this 12 millimeters? Well, from here to here we go. 1, 2, 3, 4 to get to our central fringe. 5, 6, 7, 8, 9. So there are 9 fringes occupying 12 millimeters. So there is 12 millimeters of distance per 9 fringes. And so if we divide that, we'll get, that there's 1.3 repeating millimeters of distance between each fringe, and that's what x is. All right, substituting in the wavelength, the value 2.8 meters for d, and this value for x, we should be able to calculate the separation. So lambda equals ax over d. Because we want to know a, the separation between the two slits, we can multiply both sides by d over x. And that's going to make a the subject, and it's equal to d times lambda over x. D was 2.8 meters. The wavelength, 4.48 by 10 to the negative 7 meters. And the distance x that we just calculated, 1.3 repeating millimeters. You can see that these meters will cancel, and we'll be left with meters of separation, the distance between the slits. 2.8 times 4.48 times 10 to the negative 7 meters of wavelength divided by 1.3 repeating millimeters gives us 9.4 by 10 to the negative 4. Meters is how far apart the slits are. The laser is replaced by a laser emitting red light. State and explain the effect on the interference fringes seen on the screen. So it's asking about the effect on this quantity x as we change the wavelength of the light. Now, red light has the longest wavelength, right? And so we're increasing the wavelength. Well, how is x going to change? If we just think about our equation up here, lambda equals ax over d, we're not changing the separation distance a, we're not changing the distance to the screen. So if we make the wavelength longer, then the separation between the fringes is also going to go up with it. It's going to also increase in order to keep that equation equal. So as wavelength increases, the distance between the fringes also increases.